Okay, good morning everyone. We are now in our lecture 3. Still we are in introduction. So I have no idea when we can escape from this chapter 1 introduction. This is a long introduction. So anyway, let's go. Uh, First of all, let's try to review our previous lecture 2. So our lecture 2 was devoted to the introduction of CMOS logics. So the main topic was complementary CMOS gate. So in this family of CMOS logic, we have two circuitry called pull up and pull down. So there was part pull down. And of course, this pull down is connected to this ground, and pull up is connected to VDD. Of course, this pull up and pull down are controlled by input signal, of course. Yes. So depending on our input signal, pull up and pull down can be either turned on or turned off in its entire sense. And here we have output. So essential point of this complementary CMOS gate is these pull up and pull down circuitry are made following the rule of conduction complement. So simply speaking, when we have a certain input signal, then only one of our pull up or pull down circuitry is turned on. So for example, when pull up is activated, then our output is just VDD. And if we have pull down activated, then automatically this pull up is disenabled, and we have ground as our output signal. So following this one, we can build many different logic gates like inverter, NAND, NOR, and any kind of logic function can be calculated or implemented. So by taking this complementary CMOS gate style. Okay, so that was the first one. After that, we have our last part of our previous lecture was devoted to the pass gate. So let me introduce or let me review our discussion once again. Transistors can be used as switches. Everybody understand, but for example, let's think about an MOSFET. Here we have an MOSFET, and if we apply VDD, so logical value 1, then we understand source and drain of our MOSFET are connected. Yes, that is the case. When we have 1, then source and drain are connected. But please note that this means that 1 means that the difference between gate and source should be close to logical 1. VGS should be close to VDD. That is meaning of logical value 1. However, now let's say that if we have here logical 1, once again, then although here we have gate voltage close to VDD, but source is also close to VDD, then what will happen? Then actually VGS, which is defined as difference between gate voltage and source voltage, is close to 0. So the ideal case is just passing our logical value 1 to this node, but unfortunately it is not the case. So N MOSFET is not that good to pass our logical value 1 from one terminal to the other terminal. So here one another means that source and drain. On the other hand, if we have a logical value 0, then in this case it is quite good because this is VDD and this is ground, so difference between them is really close to VDD. So our transistor, MOSFET transistor, is fully turned on, then it can make our drain terminal as also logical 0. So simply speaking, although transistors can be used as switches, but N MOSFET is only good for passing logical 0. Quite similarly, P MOSFET is only good at passing logical number 1 when it has a logical
VGS가 0이 되면 그 트랜지스터가 꺼지는 건가요?
Yeah, sure. Okay, so you have to understand this one. Transistor VGS. When VGS is, let's think about several cases. When this is a VDD, it is certain that our MOSFET is fully turned on. And when VGS is 0, and it is certain that we have completely turned off transistors. Then what happens in between? So your question is what happens? Actually not your question, but anyway, it is certain that when you have VGS equal to 0, then it is true that we have completely turned off a transistor. And here, when VGS is beyond threshold voltage, then still the transistor is turned on. And when we have VGS smaller than or lower than VGS, then it is turned off. I mean that let's make some concrete example. Like assume that we have VDD equal to 0.7, and let's say that our threshold voltage is happen to be 0.2 volt. Simply speaking, when you have VGS equal to 0.7, your transistor is turned on, and even when you have 0.7 0.3 volt, still you have turned on transistor. However, if you have 0.1 volt as a VGS value, then your transistor is now turned off. Of course, 0.0, yes, there is no way to turn on our transistor. Okay, so are you with me? Okay. Usually, for M MOSFET, this VGS is a positive number, positive 0.2, something like that. So usually we have the rule like VTH should be set as just a fraction of our VDD. When we have a VDD, for example, 1 volt, 1.5 volt, then there is a range for desirable VTH value. But point is, for N MOSFET, anyhow, our VTH is intentionally adjusted to have a positive value, a meaningful positive value. So this is quite important property, because it means that, as he asked once previously, only when we have VTH threshold voltage as a positive number, then when we apply 0 volt, transistor is turned off. So now we can use 0 and VDD as indicators for on and off. To most of you, this seems to be quite natural, But unfortunately, for many technologies, it is very difficult to have positive threshold voltage. Mhm. So it sounds quite weird, but there are many devices, many transistors, technologies whose threshold voltage is actually lower than 0. It means that even when you apply Vg equal to 0 volt, your device is not turned off. And when you apply Vgs equal to Vdg, then it is also turned off. Therefore, it is not that good for our digital application. CMOS technology is quite good because our 0 and 1 or 0 and VDD can be clearly defined as on and off state. Okay? So, however, for many other alternative technologies, it is not that certain to have positive VTH value. Okay, so that was a good question, and let's come back. So where were we now? So transistors can be used as switches, however, they are not perfect passing our signals. One has advantages for sending 0 and one has advantages for sending only 1. So the point is we wanted to have good switch to good at passing 0 and passing 1. Then how can we do that? So let's just say that we have a control signal. Yes, here we have a control signal, and when control signal is 1, then what we wanted to have is, okay, 0 is well passed. Even though we have here 1, we wanted to pass it quite well. How can we construct such kind of thing? If we just use M MOSFET, then it is not possible. So let me just show you the impossibility. So if we have M MOSFET only, and let's just say that this control signal is attached to the gate of our N MOSFET, then what will happen? If we have logical 0 and control signal is high or logical 1, then it is good to send our 0 input to the output. Good. But if we have 1, then it's not that good. So it's not perfect. On the other hand, let me just consider another one. We wanted to send our signal to the output only when control signal is 1. So in that case, think about this one. We have also P MOSFET here, and since control is 1, then inverse of control would be 0. So if we apply the inverted control signal to the gate of P MOSFET, then what will happen? Okay, now this P MOSFET is turned on once again. Then it is good to send logical value 1. So are you with me? So think about two cases. We can consider input 1, input 0 case. So input 0 case, now input 0 case, this path becomes activated. So in this case, this path is activated. And in the case of logical value 1, although N MOSFET is not very much effective, but fortunately P MOSFET is very effective to pass our input signal. So by combining them in a parallel way, then we can build a certain logic gate which is quite good to pass the input signal to the output signal. Okay, so are you with me? We are now talking about control signal of 0. Previously, we have considered the control signal equal to 1 and its inverse is 0. How about the opposite case? Control signal is 0 and of course its inverse is 1. In this case, our N MOSFET is turned off and our P MOSFET is now turned off. So our input node and output node are effectively isolated because in practice they are connected through this N MOSFET and P MOSFET. However, both of our N MOSFET and P MOSFET are turned off, so there is no way for conduct current between them. Okay, so now we can summarize this way. If we have two parallelly connected N MOSFET and P MOSFET, of course, their gates are constructed as taking the control signal and inverse of control signal. Then its behavior like this. When control signal is 1, then it is just pass of input signal to the output signal. So then the rule is like this. Then when we have a control signal equal to 0, then this is just disconnected. That is the simple circuit shown here. So now we can say that so now let's start today's lecture. So now we can say that, oh, here we have control signal, and when control signal is 1, then input is just copied to the output, and when we have input signal 0, then Y output is not related with our input signal A. That is the action of our previous test gate. So this one, please remember this one. When we have a control signal equal to 1, it just copy our input to the output, and 0 isolated. Let's go to this one. Then truth table can be drawn when enable signal is 1, then input is copied, and enable signal is 0, then Y is not related with our input signal A, and here Z means a floating state. Why it is called as a floating? So in this case, when we have enable equal to 0, then now we have well-defined A, and our Y is not connected to A. There is no way for Y to have a concrete value. It is not connected to A, it is not connected to ground, it is not connected to VDD. So we have no idea. Of course, in reality, this Y is once again connected to other circuitry. So other circuitry will determine the value of Y. But at least considering only this system, then this Y is not connected to anywhere. So it is like floating over the sea or over the river. So you can see that now the previous circuit called as transmission gate, the one having N MOSFET and P MOSFET and oh sorry, careful about here we have bubble for P MOSFET and enable bar and enable. Then this is called as transmission gate, and this transmission gate can be used as this to realize this truth table, and it is called as tri-state. Why it is called as tri-state? Here tri means three state. So usually, for example, when we come back to our previous complementary CMOS gates, its output Y can have either 0 or 1. There is no other choices for its output value. However, when you go to this tri-state gate, in this case, we can have 0 and 1, and another possibility is the third logical state we can have is the floating state. So it is not directly related to the input signal. Quite good, but here I wanted to say that it is non-restoring. What was the meaning of the terminology like non-restoring? Non-restoring. Then what was restoring? Let's think about restoring. So representative example was this inverter, CMOS inverter. Let's say that you have 0.1 volt, seemingly quite weak signal, weak 0. However, following the CMOS inverter, then what was your output? Your output was exactly close to VDD, not degraded one like VDD minus 0.1, because it is weak by amount of 0.1 volt, so output is also weak by amount of 0.1 volt. If we have such kind of thing, then we call it as non-restoring. However, we all understand CMOS inverter doesn't play in that way. It plays in this way. Even though our input is weak, but it is restored by the action of our inverter, so our signal becomes now strong once again. In that case, we call it as just restoring. Good. So although once your signal become weaker due to unwanted signal called noise, however, after action of this logic gate, now your signal becomes once again strong and healthy. So this one is called as restoring, and it is quite good to have immune to our noise signals. That is quite a desirable property. So transmission gate can act as a tri-state buffer, but unfortunately it is non-restoring. So what does it mean? So let me just consider once again. If we have, for example, 0.0 volt logical 0, then it is certain that we have 0.0 volt. Good. But point is, when we have 0.1 volt weak logical 0, then what will happen to this system? Everybody understand now? In this case, for logical, the value for logical 0, then although we have both of N MOSFET pass and P MOSFET pass, which one is activated? Only the N MOSFET pass is activated. So are you with me? So the P MOSFET is not that good pass our logical 0, so it is not activated. But N MOSFET is good at passing logical 0. So now it can pass our logical 0 to the output. However, it does not map our 0.1 volt to 0.0, the desirable value. But instead of that, it just copy the value. So if we have a small perturbation from or fluctuation from 0, then it will be just copied into the output. Is it good or bad? So from the viewpoint of a digital system, always we must have a clear distinction between logical 0 and 1, and if we have a weak signal, then it should be recovered or restored. So in this sense, it is not that good to have this non-restoring property. So another possibility to make this tri-state is not tri-state buffer. So here tri-state buffer means that here when we have enable signal, when enable equal to 1, then we wanted to have y equal to a. This is called tri-state buffer. However, when we have a tri-state inverter as shown here, then we have bubble here. So when enable equal to 1, what we wanted to have is now y is bar of a, so not or inverse of a. So are you with me? When enable signal is 1, then it is just to act like a normal inverter. And only when enable signal becomes 0, then it is acting as just a disconnected line. Then how can we do that? If we think about this way, then now you can understand this is a good solution. So please have a look at this case. Enable equal to 1. Enable equal to 1 case. Now we must have just a normal CMOS inverter. So now let's have a look at this one. Here we have enable signal for N MOSFET. And here we have enable bar input for our P MOSFET. So let's say that enable equal to 1. Then what will happen to our N MOSFET and P MOSFET? Our N MOSFET will be turned on. At the same time, our P MOSFET is also turned on because its gate is biased with bar of enable signal, not just enable signal. Okay, so when enable signal equal to 1, then both of our P MOSFET and N MOSFET are turned on. Then now only thing remaining is this P MOSFET and this N MOSFET driven by the same input signal. So now simply speaking, here we have A, and that is connected to the P MOSFET here, and that is connected to N MOSFET here, and in between we have just Y. Of course, here we have a P MOSFET and N MOSFET, but they are all turned on, so we can neglect them located here and there. So now when we have an enable signal with value 1, then its circuit schematic can be simplified as that of CMOS inverter. So now we understand, okay, when enable signal equal to 1, it behaves just like a CMOS inverter. Then now let's go to the other case. Enable signal now becomes logical value 0. What will happen? Now this guy turned off. At the same time, this guy is always turned off. So from the viewpoint of our output node Y, now it has no path, conduction path toward VDD or ground. So Y is just insulated from VDD or ground. So now we have, okay, now we have when enable signal equal to 0, then now it becomes just in the floating state. So now it produces once again a restored output. So let me just think about the case once again. When we have a value, weak a value, however, still we will have completely recovered restored value VDD. So good. The only thing we have to keep in mind is this is tri-state inverter. So we are not having the tri-state buffer. So that is the difference. But anyway, it is good to have this kind of restoring circuit. And I wanted to say that this circuit certainly violates the conduction complement rule. Please note that when we have a conduction complement rule, then only one of pull-up or pull-down circuitry is turned on. However, we intentionally wanted to introduce the third state called Z over floating. So if our circuitry exactly follow the conduction complement rule, then this state is not possible. So intentionally we have to disobey this or break the conduction complement rule. So that is quite easy to understand. Now let's go to the multiplexer, or sometimes we call it as MUX. So this is the simple 2-to-1 multiplexer. 2-to-1 multiplexer means that here we have two different signals, and this is also controlled by our signal S. So when S is 0, then this path is selected, and when S is 1, then this another path is selected. So we have two candidates. Oh, I want to go there. Or, oh, I want to go there. There are two candidates, and this is signal. Yes, select one of them. Then how can we implement this logical function using our digital circuit? Okay, so but before talking about that one, let's just repeat it. This is a truth table of a 2-to-1 multiplexer. When S equal to 0, then think about it. Then we say that the D0 is selected. So D0 is selected. So D0 is copied to the Y. So whether it is 0 or 1, that doesn't matter, because this is just disconnected, not selected by our signal. And when we have signal equal to 1, then now on the other hand, this D1 is selected, and this D1 is just copied to the Y, and the value of our X or our D0 doesn't matter. Then how can we implement this one with our digital circuits? That was our previous question, and we now understand this one. From the viewpoint, from the viewpoint of D0 to Y case, this is a kind of tri-state. I mean that when S equal to, oh, so I think that it is better to think about this one, this path. First of all, think about this path. The path from D1 to Y, then this path can be regarded as just a tri-state buffer. Say, when we have S equal to 1, then D1 is copied to Y. And S equal to 0, then Y is nothing related with our D1. It has no influence on Y. Then please note that this is actually the action or operation of our tri-state buffer. Okay? When controlling signal or enable signal is 1, then it becomes a buffer. And when it has 0, it means that enable signal equal to 0, then this becomes floating. Quite similarly, we can say that this path, the D1 path, is also treated as a tri-state buffer, but the difference is now when S equal to 0, it is working as a buffer, and when S equal to 1, now it is in its floating state. So simply speaking, this path, the D1 path and D0 path, are controlled by the opposite signals. So if we make it that way, then we can implement this one. For example, let's think about, for example, this one, implementation with, okay, so first of all, let's think about this one. The implementation with the transmission gate. So although we have 4 transistors, first of all, just to concentrate on this D1 path from D1 to Y. Then you can find that this is nothing but just a tri-state buffer controlled by our S signal. When S signal equal to 1, then it is working as a buffer. And S signal is 0, then this path is deactivated. So please think about the path from D0 to Y. Then when S equal to 0, then now this S signal is connected to the P MOSFET, and N MOSFET is driven by our S bar signal. Then now when S equal 0, this upper transmission gate is not switched on, and only when it has S0 signal it is turned on, and D1 is connected to Y. So this is the possible way to do that. Okay. Of course, since each of them is non-restoring, so therefore the system, the multiplexer implemented using transmission gate is also non-restoring. So if we have a small perturbation for D0 or D1, that will be just copied into our logical value Y. Okay, but anyway, then let's think about this implementation using tri-state inverter. So let's think about the case where we have S equal to 1. Then what will happen? Since S equal to 1, okay, this one is activated, and S bar is 0. So also P MOSFET is activated. Wow. So now we have one thing. And here we have S bar equal to 0. So this MOSFET is turned off, and this S is 1, so P MOSFET is driven as logical value 1, so also this P MOSFET is off. So from the viewpoint of our D0 signal, let's think about it. Okay, I wanted to go to the output Y, and it goes in that way, it goes in that way. However, now its path toward Y is disconnected. Oh, so D0 doesn't have the electric path toward Y. So D0 is completely isolated from Y. However, in the case of D1, now it has this path and this path and this signal just connected to our connected through our S and S bar and MOSFET, P MOSFET. And when you have a look at this one, then the operation is when S equal to 1, then Y is what? Just D1? No, it is working as an inverter. So now we have Y equal to D1 bar. So, what you want to have this kind of thing. This is 2 to 1 multiplexer. We just want to copy D0 to Y or D1 to Y. However, implementation with these tri-state inverters just invert once again. So in this case, instead of that, here we have 1, 0 and 1, 0. However, it is quite easy for us to invert this signal once again using CMOS inverter. So sometimes the important one is this selection capability. Once you select D1 or D1 bar, then you can easily generate D1 or D1 bar respectively by taking these CMOS inverters. Okay. So also when you have larger multiplexers, for example 4 to 1 multiplexers, you can use multiple multiplexers to one of them. For example, if we have 4 candidates, oh please select me, then it is easy to say that, for example, when we have 0 and 0, what will happen? If we have 0 and 0, then this guy will be selected and this guy will be selected. And now we have a second level of multiplexer, and still the S1 selected this path. So the activated path now becomes this one, and here we have twice bubbles here. So now Y becomes D naught when we have a signal of a 0, 0 signal. Okay. So do you have any questions? So this is the content in our chapter 1 introduction about CMOS logics. Of course, our textbook considers also certain discussion about sequential logic family. However, I have omitted that one because we will postpone the discussion on the sequential logic to the end of our lecture, our semester. So we will revisit this one if time allows. Then also, unfortunately, this long chapter 1 contains also discussions about how can you fabricate the CMOS device and how can you lay out our CMOS circuit. So I will also talk about this content. So this is a long introduction. So we have many slides taken from our textbook, but let me just quickly cover this one. Yes, you are now looking at the inverter. So how can you visualize your inverter in your mind? So for some guy, maybe this is your inverter. I have A and I have Y. This is your inverter. And to some of you, maybe this can be your inverter. A, Y, VDD. This can be your inverter. And to some guy, this can be also your inverter. So this is your A and your Y. Then what is it? So you understand the conversion from here to there. Up to now we have discussed it in that way. So logical value 0 is converted to 1. Logical value 1 is converted to 0. This is converted to voltage 0 volt and voltage VDD. And this one is corresponding to voltage VDD and voltage 0. Now, in this level, we have N MOSFET and P MOSFET selectively reacting to the gate signal polarity. So when we have VDD, now this transistor is turned on. So we have a pass from Y to ground. So Y has a value of 0 volt. Everybody in this classroom now understand this kind of action. Then however, this symbol, N MOSFET symbol, P MOSFET symbol, is just only in our brain. Then how can you make a silicon chip from this kind of schematic? So this cross section shows how can we make our inverters, the simplest circuit, into our silicon chip. So now we understand this inverter has some components like A, Y, VDD, ground, N MOSFET, P MOSFET. Where can you find it? So here you can find A. This is input. Y. This is output. And where can you find the ground? Okay, you can find ground here. Where can you find the VDD? Yes, you can find the VDD here. And now the remaining things are what? Your N MOSFET and P MOSFET. Then where can you find N MOSFET and P MOSFET in this cross section? So as I told you before, N MOSFET and P MOSFET are made of just MOS system surrounded by source and drain. So you can see that here you have your N MOSFET and here you have your P MOSFET. Please have a look at it. Here we have gate and here we have substrate, and one is regarded as source and one is regarded as drain. Then please check whether our cross section is corresponding to the schematic. So its source is connected to what? Connected to the ground. Where can you find this drawing? So what you can find is, now you are looking at this part. Your source is, N MOSFET's source is connected to the ground. That is shown here. Your drain is, N MOSFET's drain is connected to this part, this one. And this is output signal Y. You are now looking at the part shown here. Then in between, you have a MOS system, substrate and input A, and you can see that this vertical structure is corresponding to this structure. So now you understand N MOSFET is correctly wired like our schematic. And let's go to the P MOSFET. Here we have a P MOSFET. The difference between N MOSFET and P MOSFET is, it is, in the case of N MOSFET, it is built on P-type substrate and it is built on N-type well, and source and drain was previously made of N plus region, and now we have P plus region, and this is the source and this is the drain. Check whether our source, P MOSFET source, is connected to the VDD. Okay, this is attached, and you can see that source of our P MOSFET is attached to the VDD. And how about drain? In the case of drain, it is attached to the output signal Y, and you can find that this is the case. Of course, you have once again MOS vertical structure here, and this MOS vertical structure driven by signal A can be found also here. So now you can see that although we have one physical reality, the silicon chip, but there are many different ways to understand it. So it is more abstract and it is much more detailed. Okay, so are you with me? Usually we are working in this class, we are working in this level. We will use this kind of view. But for today's lecture, we will talk about how can we actually fabricate this kind of structure. So I will just briefly explain it. And please note that is this the state-of-the-art device? Actually not. It is a quite old-time device. However, the reason why I explain this to you is not since it is not the most updated device, but please understand just a feeling about how can we fabricate something realistic into our silicon chip. Okay, so now what is the difference between this figure 1.34 and this one? Yes, here we have p-type substrate, and if we just go to there, then this p-type substrate is no connection to the ground. So intentionally here means that we have the connection between p-type substrate and ground. If we don't provide this substrate tab, then there is no way to connect our p-type substrate to the ground. Of course, if you are working in the laboratory, so fabricating some experimental device, then another way biasing this p-type substrate is just backside contact. So you can provide certain voltage from backside. However, this is not the way used in our CMOS technology. In the CMOS technology, we are providing our signals or powers like a ground signal or VDD from the top of our system. So we must introduce certain plugin. So usually this p-type substrate has a relatively low doping density. So if we don't have this substrate, so-called substrate tab, then if we have just to make a simple structure like this is metal and our p-type substrate, then actually this interface, the interface between metal and our lowly doped p-type substrate does not provide good conductivity. So it is not good in terms of electrical conductivity. So in order to eliminate such kind of problem, difficulty, we intentionally introduce highly doped laser. Then now the interface between this and that is improved, and also since they are all the same p-type, so the electrical connection is much better then this direct connection between metal and low-redox p-type substrate. Okay, so this is in. Of course, this is related with our biasing of p-type substrate. In the same way, we must provide a certain bias to our n-type well. So n-type well case, we have to also introduce this kind of n plus doping reason. So this one is called as well tap. Okay. So if you don't understand, then please let me know, and I can answer your question as much as I understand. Then in order to implement this one into our silicon, then we need mask. This one just shows a set of masks to make our CMOS inverter shown above. This is not a single mask. There are many different masks. For example, you can see some, I can say here you can see certain rectangle and another rectangle with a green color, and that is called as N diffusion mask. And another one, here you have a orange colored one. This one is P diffusion mask. Also you have another one like a metal one. So there are many masks are used, and usually when you introduce one additional mask, it is directly related with increase of your fabrication cost. So in reality, engineers, device engineers, technology engineers try to minimize the number of masks to fabricate your device. Okay? But this is not your role, but to them, that is critically important. So let me just briefly introduce how they fabricate this inverter, starting from the blank wafer. Blank wafer, you just buy your wafer from wafer supplier, and of course it can contain some contamination here. So before starting this procedure, of course you must clean it. Clean means that using the strong acid, you just eliminate all kinds of organic contaminations. So now you have just flat and blank wafer, quite clean. And p-type substrate, usually it has a certain given doping level. So it depends on actually your specification. I mean that there are wafer suppliers and they have given specification of their wafers, and you can just select it and buy. Okay? Anyway, not that high, this doping level. And now for the first so from now on, first we will talk about the N well fabrication. I mean that here we have a p-type substrate. P-type substrate is suitable for making our N MOSFET. But please remember that we have both of N MOSFET and P MOSFET to realize our CMOS circuit. So we have to be able selectively generate a certain N well. Okay, let's say that this is N well, and on top of it we will make our P MOSFET. Then how can we make on N well? Now we will talk about this N well fabrication or N well formulation procedure in more detail. After that, the later steps will be more quickly introduced because that is just a repetition of a similar procedure. So one is, okay, so we wanted to introduce certain oxide. So here we have oxide, Then we introduce photoresist. Photoresist is a light-sensitive organic polymer. So right now, usually that photoresist is spread spin. So simply speaking, if you have a vapor, then there is a drop of your photoresist. At the beginning, you have just some drops on top of your vapor. After that, so-called spin coater just rotate this vapor. Then what will happen? If you have a vapor and a small drumlet of your photoresist, then by action of this rotation, it will be spread out uniformly over your vapor. So right now, you have a system like silicon and silicon dioxide and photoresist, which is just widespread and without any patterning. So everywhere you have just vertical structures quite uniform. Now important step is photolithography. So previously I show you the mask, and this mask is used for patterning. So simply speaking, now you have this kind of opening, let's say, then the light comes in, and for these points, this is just blocked by our mask. Also, this is blocked by our mask. Only this open position, open window, now light comes in. Then what will happen? Previously, photoresist was there, and now it has different chemical composition. So, for example, this is solid and rigid. It's not. Now it becomes much softer. After that, so even though when we expose the light on it, but that does not immediately remove this photoresist. Now, just after we expose the light, then we have two different photoresists still on top of our silicon vapor. One is a solid one, and one is a soft one. After that, this soft photoresistor is removed. So we have a specialized chemical to remove this one. This chemical just remove only soft photoresist, and that solid one, the rigid one, still be there. Okay, so this one, when we have such kind of thing, then we say that that is patterned. So please note that previously, yes, up to here, there is no pattern error. However, by taking this post-lithography step, now our vapor is patterned, and now we have certain chemical hydrofluoric acid, which is quite strong, and it can eliminate our silicon dioxide. Okay, there was silicon dioxide, however this HF can etch this silicon dioxide. Maybe you can ask me why it is still there. Here we have still silicon dioxide. Why it is not that damaged? It is because here, of course, here we have silicon dioxide, and HF comes in. Then it will be etched out, but it is not immediately gone. it takes some time. So after some certain time later, then it becomes thinner and thinner. Of course, we have lateral etching also. However, by controlling the time and condition for this etching condition, the etching process, we can make almost vertical structure, killing or etching only vertically, and lateral etching is minimized by process optimization. Okay, so now we have, after this kind of procedures, now we have a bare vapor exposed to the air. Okay, wow, and this one is protected. So now we can do something only selectively for this open window. Please remember that what you wanted to do was n-well formulation. So now that photoresistor is its role is over. Now it's removed. After that, now we can implement the n-well, or we can formulate the n-well. It is done by this way. First, ions are implanted here. Then at the beginning, just after ion implantation, there will be N-type ions located in the surface of our vapor. After that, we introduce thermal diffusion. So simply speaking, you just put your vapor into the furnace and just bake it for a long time. Then what will happen? Then now these N-type dopants are thermally activated and it diffuses over the silicon substrate. Of course, it has also certain lateral diffusion. So that's the reason why even in this crude schematic diagram, you can see that the range of your N-well is not perfectly matched to your opening. So although your ion implantation more or less having certain range of like this, of course it has slight also diffusion or overlay here, but also thermal diffusion introduce lateral diffusion. So that's the reason why we have N-well slightly wider than opening of our N-well. Okay, so are you with me? Anyway, at the end of this procedure, now we have p-type substrate, and also we have N-well, whose N-well density should be larger than p-type. So now, then oxide is removed because it is no longer required. Then now we have, so compare this one and our very first blank. Oh, sorry. Let me just quickly go through. Compare with our blank vapor. Starting from this p-type substrate with various steps, now we have the vapor where selectively N-wells are formulated. Wow. Then the later step will be, okay, I will make an MOSFET here, I will make a PMOSFET here, and later they will be connected to each other. Okay, so unfortunately we have only 4 minutes left, so let me just go spend my remaining 4 minutes and let's wrap up today's lecture. So now, up to now, we just prepared the p-type substrate and n-type substrate, and in order to make your MOS system, then you need something like this. Of course, you must have substrate, p-type or n-type. You must have substrate, and also you must have O. This O is corresponding to your O here. S is here. So now in this slide we are now looking at the steps to make our O oxide, and the quality of this oxide is critically important. Please note that how can we turn on and turn off our transistor? What you do is apply certain gate voltage, and depending on this gate voltage, you collect electrons in beneath of this oxide layer, or just remove these electrons. So if we don't have high quality oxide here, then this MOS operation doesn't play a role. So it is quite important to have a high quality oxide in this step. So it is critically important. And also another quantity or another figure we have to be keep in mind is, for example, here we have an interface between silicon substrate and silicon dioxide. So although silicon dioxide is oxidized form of silicon, anyway they are different materials. So therefore, here we have one material and another material, and here we have interface, and this interface must have many defects, and these defects, structural incomplete things, they are playing quite an important role in the electrical characterization. So we wanted to minimize the number of defects in this interface. So anyway, the quality of this oxide layer is quite important. So now we introduce very high quality, extremely thin gate oxide here. After that, we introduce a polysilicon layer. But I wanted to say that right now, in the state-of-the-art device, we do not use polysilicon any longer as a gate material. The polysilicon is shown here only because this lecture material is based on somewhat old technology. So please note that right now, the state of the device, instead of this polysilicon gate, we are using metal gate. Please understand the outdatedness of this presentation material. Well, anyway, the time is up today, so we will continue to discuss this fabrication on Thursday. And I wanted to say that although in our original syllabus there was scheduled to have an online lecture or pre-recorded video lecture, however, I adjusted my business travel, so we can make offline lecture. So please visit this lecture room once again on Thursday. Okay, do you have any question on today's lecture content? Okay, if not, then let's wrap up today's lecture.